Hello everyone, my name is John Onofrey. I'm an assistant professor at Yale University, and my interests lie in applying machine learning technology to medical image analysis problems. I also worked as a software engineer for 4 years prior to returning to school. In this segment, I will discuss some of the practical issues that artificial intelligence and machine learning applications face during the medical software lifecycle. Compared to the traditional software design lifecycle, AI and ML applications face a unique set of requirements. As I'll discuss further, the training data is intrinsically tied to AI/ML model development, and requirements must be accounted for. Requirements must also address any special hardware constraints. For example, in deep learning applications, are GPU resources needed during the training phase, or the production phase, or both phases? Finally, AI/ML applications are limited by the training data that the models use, and these limitations on the system must be accounted for. For example, if an algorithm only sees training data from a specific age range, then the algorithm can only produce outputs for that same range. Risk assessment in AI/ML applications must also be considered in a different way. These algorithms are essentially black boxes where limited information about the model comes from inspecting the components of the model. For example, in deep convolutional neural networks, the weights of any individual convolutional kernel tells us very little about the model and its decision process. The DIN-spec software specification, previously discussed by Professor Papadimitriou, lists 2 sources of risk for AI/ML applications. These include distributional shifts and adversarial attacks, both of which I will discuss next. It is important to note that cybersecurity also falls under the scope of risk assessment. To illustrate an example of distributional shift, I'm going to highlight an example from some of our previous work that involves prostate biopsy. Now, this goes back to a previous task that was highlighted by Professor Papadimitriou. In this task, suspicious prostate cancer is first identified in magnetic resonance imaging by a radiologist. A urologist then performs a needle biopsy to perform the sample. Sorry.
We're okay. Just pick it up from it right from the as you went to the slide. You just leave the slide.
Yep.
Leave the slide
Good.
out and just go right back to it.
To illustrate an example from, sorry. To illustrate an example of distributional shift, I'm going to revisit a previous task that was mentioned by Professor Papadimitriou. And this task involves image-guided prostate biopsy. In this task, a suspicious prostate cancer lesion is first identified in the magnetic resonance imaging by a radiologist. A urologist then performs a needle biopsy to physically sample the prostate tissue. This sampling is performed under ultrasound image guidance. The challenge here is to align these 2 different imaging modalities. Here, the Artemis image-guided biopsy system performs a surface-based registration to align the MRI to the ultrasound. And some of our previous work has addressed this problem. This registration method relies upon a segmentation of the prostate gland in both the MRI and the ultrasound, so an important component is automatic segmentation of the gland. Here, performing segmentation of the MRI is where we can find a problem with distributional shift. In the real world, different hospitals and different care centers have different kinds of equipment, and any kind of algorithm should be able to accommodate these kind of situations. Here, we have MRIs from 2 different institutions acquired on 2 different scanners. While these images all appear to be prostate MRIs to a radiologist, a deep learning algorithm sees them completely differently. If we examine the intensities of these images, we can see that the 2 scanners have different intensity profiles for the prostate, with the red histogram showing data from Stanford and the blue histogram showing data from Yale. And full details from this example can be found in one of our previous papers. In an experiment here, we can show that the differences in these 2 intensity distributions can have a dramatic effect on segmentation performance. In this case, 2 models were trained. Each model used data from a single site, and the model was then tested on data from the same site. And here we can see results that these models worked very well on data from the same site. But when testing it on data from the other site, the models then ran into problems. As you can see, using data trained from Yale and testing it on data from Stanford, the model performed a little bit worse. But when we actually used a model trained from Stanford data and tested on Yale, the model actually had median performance of 0. The second adversarial The second example highlights risk from adversarial attacks. Here we see example natural images where a single pixel in each image was perturbed and the image classification model gave an incorrect prediction. For example, changing only a single pixel on the image of the airplane caused the model to incorrectly classify this image not as an airplane but as a dog. In medical imaging applications, an adversarial attack could actually come from the patient unintentionally. For example, any implants that the patient might have could result in small imaging artifacts that drastically affect model performance. For continuously learning AI ML applications, there are additional risks. These include quality control of new training data. This must be of similar quality to the original training data. New training data may also introduce problems of bias, where performance may negatively drift away from old data and favor performance of newly seen training data. These drifts can also be unexpected for users, especially in cloud-based systems, where updates to models occur in the cloud and end users are completely unaware of this process in the background. AI/ML applications also have a unique set of software design requirements. In traditional software design, we have explicit software requirements, and code can be broken up into smaller units, and each unit can then be tested one at a time. And we have explicit tests such as 2 + 2 = 4. However, in AI and ML, we only have a black box to work with. Here, the algorithm itself is one giant software unit, and we can only test the overall module as a whole. And there are no known answers for simple things like 2 + 2 = 4 in these cases. Instead, we have to evaluate model performance against expert performance. Software design and AI/ML applications can be broken down into two separate workflows. Here, we really have two different workflows, training a model and then using the model. It's important to note that in AI and ML, that training code does not become part of the final product, yet it is intrinsically linked to the model's development, and therefore we capture this as a distinct workflow. Finally, because the training data is so intrinsically tied to the model through the training process, we need to manage this training data appropriately. In AI/ML, quality control of the data is also critical. When developing these applications, we need to ensure reproducibility of training data in the training process itself. For example, we can control what random seeds are used during the training process for reproducibility. This can result in reproducible initialization of model parameters, for example, the weights and biases of a deep network, reproducible cropping or patching of data if it's used, or reproducible data augmentation strategies that use random noise or geometric distortions to transform the data. But the idea is to do this in a reproducible way. Ideally, any preprocessing code, for example, normalization or scaling of the data, should be shared between both the training and the testing workflows. And this is a way to maximize the reproducibility of the code to make sure one thing happens in the training process, the same thing happens in the testing process or the production phase. Again, training data is a key component, if not the key component of any AI and ML application. And we must treat this as such for software design and development process. While the training code and the hours of computation time spent on training iterations may never show up in the final product, this overall process must be properly designed and maintained within the training workflow. Finally, deployment of the system may require special hardware such as GPU resources as cloud-based systems. Once the system has been trained, we then need to test it, and we must have to be aware of certain limitations of the trained model. First, the training data may not be representative of the data seen in the real world. And we cannot verify this until we actually test the model in the real world setting with actual data. And when testing, we must continuously monitor performance post-market over time to look for things like performance drift. For further discussion of this, here's Professor Christian Kastner.
The training and the test data is from one distribution. It shifts a little bit. Like in the medical setting, it's often you have training data in some hospital with a certain population in that region where that hospital is, and it may not generalize to a different hospital in a different region where your demographics are different, where maybe you have slightly different scanner or the scanner is not calibrated the same way in medical imaging, right? So you have these drift issues. So it's very common that you actually test in production. So for that, you need to have some way of measuring how you're doing in production, kind of continuously observing. You make some predictions. For example, how often does a radiologist agree with your prediction or disagree with it? And if you see that this kind of goes off the charts, like you're really bad in this area, then you probably don't want to continue using this in production. You probably need to collect more data in this area, retrain. And that's another challenge in building these machine learning systems, is that you kind of need to continuously think about, prepare that you need to continuously retrain these things, collect more data. So it's not you release it once and you're done most of the time. You want to monitor them in production. You want to update them. It's not that we have never done this with traditional software systems. Those also get updated all the time, but it's a different quality. And because we kind of don't have a good specification, right? It's not that the specification changes, it's the data distribution somehow changes, for which we often don't have a great handle of how to do this, how to detect drift, how to characterize the data, and so on. That's often much more challenging and requires a lot of planning and building the infrastructure to detect things in production. And so
With all of the challenges facing AI and ML applications in medicine, another way to think about this is to treat them as unsafe components. Unsafe components are modules that will fail on occasion. Here, a 99% accuracy also means a 1% failure rate. Therefore, we must design the system to be robust to failures. Again, here is Professor Kastner with an analogy to illustrate this point.
the example here is of a smart toaster where you may have a system, you put machine learning in there for the toaster to decide automatically how long to toast something. There might be a camera and a temperature sensor in there, right? And based on what it sees of what's toasting here, it decides, should I continue toasting or should I stop, for example, right? That could be a machine learning model that you could train. Now, the machine learning model could be wrong, but at the same time, you don't want to burn down your kitchen, right? If it occasionally burns your toast, that's probably okay, but you don't want it to burn down your kitchen. So now you have this component in there that decides, should I continue toasting? And some of those answers might be wrong. I can invest a lot in making that machine learning prediction better, but it's still like maybe from 95 to 99.9% accuracy, but there's still this 0.1% mistakes that might happen. I still don't want it to burn down my kitchen. It's really easy to make toasters safe outside of the machine learning system, right? If I think of the entire system where machine learning is a component, I can put in other safety mechanisms. I can have a non-machine learning component that looks at the temperature sensor and says, if it goes above a certain limit, shut down the thing, independent of what the machine learning model says. I can even go a step further. I don't even need software. It's common to build in a thermal fuse into these systems. So a small electric component that if it gets too hot, it simply shuts down power to the toaster, right? So here we have a safety mechanism that's outside of the model, the machine learning model, right, that checks on it, and kind of just, we still burn the toast occasionally, but we avoid the worst case consequences, right? And I think in a lot of machine learning systems, that's really what you really want to think about, probably also in medical systems. How do I get a human in the loop to check the answers? How do I detect kind of wrong outcomes and consequences? And that's probably not the model makes a wrong prediction. The model may make a wrong prediction, but you want to avoid that prediction leads to bad outcomes down the way, right? And that's really system design, system thinking to some degree, classical software engineering, user interface, and human AI interaction design, like lots of areas in this area where you can, in this field, where you can really think about how do I design this to avoid bad outcomes.
In conclusion, the software development process for AI and ML applications is a bit of a switch from the traditional software design paradigm. Here, the training process and the testing process are split into distinct workflows. And because the training data is intrinsically tied to the training process, this must also be accounted for in the software development process. It is also important to keep in mind that any training data used by the model may not be representative of the data seen in the real world. So expect failures, and also expect that you have to continuously test this model in the real world and continuously evaluate it. Finally, to create any practical, usable, and reliable AI and ML applications in medicine, these algorithms should be designed to be robust to failure from the start. And this really all begins with a good software design.